So my talk, even though the title suggests that it will be some kind of review, the main message that I want to convey is that in order to study some of the systems that people are considering these days from a Hamiltonian perspective, the usual approach by Dirac is actually not the best way to proceed. There are best methods which are equivalent, so we can prove that they are equivalent, but they have a more distinct, a different flavor. They are more geometric, and this is not a matter of point of view or a matter of legal viewpoint, but it is really a practical matter. So there are in many concrete examples, there are some problems that you can avoid if you use these other geometric methods instead of trying to copy Dirac's algorithm. Okay? So this short summary of my talk, I will very quickly motivate why we are interested in Hamiltonians. I will tell you something about singular Hamiltonian systems, in particular H theories are singular Hamiltonian systems. I will describe quite quickly what this other geometric method, which is actually quite old, how it works and what it means. And then I will show you a couple of applications. One of them is a very simple field theory in a space-time with boundaries. One of the contexts where these geometric methods are superior is the context of field theories in manifolds with boundaries. And another application that I will discuss is really what you get from the Holst action that you can use to derive the Ashtekar formulation. How the Holst action has been studied from Dirac's point of view. When we go through the analysis of the constraints there, it really gets very complicated. So at the end of the day, even though you find the correct result, it's difficult to disentangle what you get. Whereas if you use these other geometric methods, you can actually arrive at an equivalent form of constraints, which is actually much, much nicer. In fact, once you see that, you realize that there are other conceivable ways to arrive at the same result, which are very suggestive. So I will actually tell you how you can do, how you can proceed in that way for this particular example. And also I will show you a new result that you get when you follow this path, which is what we call the quantize formulation for the Lorentzian GR. This is a Hamiltonian formulation for GR, which is, of course, equivalent to what we have, but it is much nicer in some respects. And I will show you also that one of the things that you can get from that very, very quickly is the Ashtekar formulation for Lorentzian derivation. At the end of my talk, I will say something about functional issues. This is actually quite an interesting subject, but I don't have enough time to cover it here. But it may, in my belief, it may play a relevant role if you really want to advance in the use of Hamiltonian methods. Okay? So, motivation by Hamiltonians. There are several conceivable ways to quantize field theories, but one of them, which is very traditional and is very useful, is to rely on a classical Hamiltonian formulation of field theory. From a point of view of mathematics, if you want, one of the nice things about Hamiltonian mechanics is that it has a very distinct geometric flavor. And in that sense, if you come from general relativity, then it's easy to think about Hamiltonian mechanics if you take a geometric perspective. In the case of singular Hamiltonian systems, which is the main subject of my talk, if you use, as I said, if you use a geometric perspective, then things can be understood much, much better than if you use Dirac's algorithm. If you go to the book of Dirac, where he explains his method, the language that he uses there is purely mechanical. He's always talking about evolution, about the stability of constraints under evolution. So even though the physical ideas that you are using there are quite clear, it has, I mean, from a geometric perspective, it's actually very difficult to understand. It can be done, but you really have to think about it very carefully. And in some instances that can actually be confusing. Okay? So, very quickly, let me review how you get at the Hamiltonian formulation. So you have a field theory. First of all, if you want to discover field theory, you have to choose a space of field, okay? Which you interpret as an infinite dimensional manifold. And of course, whenever you have to deal with infinite dimensional manifolds, there are functional analytic issues that are relevant, because if you model, you have to model your manifold on some infinite functional space. The images of the charts in infinite dimensional manifolds must be some kind of functional space where you have to specify in concrete terms some structure. For example, if you want to have Banach manifolds, you have to specify the norm, because in infinite dimensions you can have non-equivalent norms. That doesn't happen in finite dimensions. So somehow, when we do physics, we feel that these functional things are superfluous in the sense that, well, we will just work with a kind of regularity that we need to make sense of the field equations, and that's it. But this can be relevant, depending on the kind of norms, for example, that you use for other topologies. You may end up with something which can be easy to deal with, or something which can be very complicated from a mathematical point of view. Okay. Well, once you have chosen this configuration space, the traditional way to produce mechanics is you go to the tangent bundle, you define a real functional tangent bundle that you call the Lagrangian. Now you have to introduce a suitable space of paths in order to write the action. For example, standard choice is something like this. So you pick paths that go from one configuration to some other configuration, that are called Q1 and Q2. The paths start at time t1 at Q1, and then they end at time t2 at Q2. And you have to demand some kind of regularity. So it's the usual thing is to demand that these functions are, these curves are twice differentiable with continuity. Now, with the help of the Lagrangian, you define a real function in this path space, which is called the action, and you use that as an interval where you use the Lagrangian that you're going to use there. And your dynamics is given by the stationary points of this action, which are given by the order Lagrangian. Okay. Now, very quickly, how do you go from the Lagrangian to the Hamiltonian? Well, you have your configuration space. You can build either the tangent bundle, or you can build the cotangent bundle. An important difference between the tangent bundle and the cotangent bundle, as you all know, is that in the case of the cotangent bundle, there is a canonical symplectic form. There is some structure there, the two forms there, that you can build just with the elements that you have in your cotangent bundle. Okay? There is no such a thing in the tangent bundle, of course, but of course you can put them by hand, and that is useful in some circumstances. But in the case of the phase space, you have that. Now, the first step to get a Hamiltonian is to define the momenta. Mathematicians often refer to this as the fiber derivative. And this is a map from the tangent bundle to the cotangent bundle that preserves the fibers. So to a point here in the fiber over Q in the tangent bundle, you associate a point in the fiber also over Q in the cotangent bundle. Now this guy there will be a corrector, so it's a dual object, so you have to tell me how it acts on vectors, and this is how this works. You take, it depends on the Lagrangian, you just compute this derivative with respect to this parameter at t equal to 0, and it gives you the definition of these two objects. Okay? Now, next step, once you have introduced these momenta, you can define a function on the tangent bundle, which is called the energy. This is standard definition. This is PQ naught minus the Lagrangian. And a very important feature of this function is that if the Lagrangian is time independent, it's easy to prove that this is constant and the parallel motion when you work on solutions of the order Lagrangian collisions. Hamiltonian mechanics. In 3 short steps, you can describe it. So now, with the help of this fiber derivative and the energy, you define a function, a real function, on the cotangent bundle. You call that the Hamiltonian. Now, with the help of the canonical symplectic structure that you have there and the exterior differential of the Hamiltonian, you define the Hamiltonian vector field by solving this equation. This is the interior product of the field with the symplectic form. And once you have this, the integral curves of this vector field projected onto the configuration space give the dynamic. Now, there is something important to point out here, which is the fact that if you look at the definition of a Hamiltonian, you have here the inverse of this fiber derivative. So, if that inverse is well defined, there is no problem. But what happens when this function here is not invertible? That is actually the definition of a singular Hamiltonian system. So by definition, will be a singular Hamiltonian system is one for which this fiber derivative is not a differential. Now this may look like a complication, but of course we know that singular Hamiltonian systems or Lagrangian systems offer many possibilities beyond those provided by regular systems, and in fact most of the field theories that are relevant for physics are actually of this type. So electromagnetism, Gambil's general relativity are examples of this. Gauge theories are particular examples of singular systems, but there are others which are not gauge theories that are singular. And actually we'll show you a simple example today. Okay? These are in particular the type of systems for which the Axe algorithm was created by him. And the point, as I have already said at the beginning of the talk in the introduction, is that the Axe method is really phrased in dynamical terms and relies heavily on the use of Poisson brackets. Now, there are circumstances where this is not a problem, but in some other circumstances you have to be careful. And one of them, which is popular these days and very important and relevant from a physical point of view, is the formulation of field theories in manifold with mandals. And actually there were a couple of talks yesterday where people have discussed precisely such types of systems. So my claim here is that the best way to deal with these things is to use a purely geometric approach. Of course, this is an old idea. I have not invented this. This actually comes from the late 70s, and the method that we have found that it is much better in many instances to deal with the systems is what we call the DNH method after Rotain, Nestor, and Hinds. And I will just tell you what the main steps of this method are, and we'll try to justify almost pictorially why it is, how this works, and then I will show you applications of this. So, the steps are the following. You start, of course, with a Lagrangian, you target bundle of some configuration space, you compute the fiber derivative, which gives you the definition of momenta. Now, very often, this fiber derivative is not onto, but it is injective. So the image is not the full phase space, but just a subset, which also very often is a submanifold. Okay? So that's a nice space. This submanifold is called the primary constraint submanifold, which in the language of Dirac, he says that, well, if sometimes you cannot write the momenta in terms of the velocities because there are some conditions, algebraic conditions involving velocities and momenta, so these conditions is what I call primary constraints. Well, from a more geometric picture, it's actually the image of this fiber derivative, what he's talking about, right? Now, the fact that if your fiber derivative is injective, it will be actually a bijection on its image. So the equation that you have to solve in order to find the Hamiltonian can actually be solved as long as you just restrict yourself to this primary constraint submanifold. So you cannot immediately find a Hamiltonian defined on the whole phase space, but you can definitely find a Hamiltonian on this primary constraint submanifold. So that is one of the ingredients that you have there. Again, from Dirac's perspective, what he says is, well, on this primary constraint submanifold, you have a unique Hamiltonian, but you don't know what happens beyond that, so you may have many extensions of that, and he actually considers a family of extensions to really study dynamics and get consistency, okay? Here, actually, you just care about the value of Hamiltonian for the primary constraints on manifold and nothing else. Now, another thing that you need is to take the canonical 2 form that you have in the phase space and put it back to the constraint, to the primary constraints on manifold. I will call that pullback small omega. And now the really key step in this method is the following. You have to find the maximum, the biggest submanifold in some sense, contained in the primary constraints submanifold such that first this equation holds. So this is the definition of the Hamiltonian vector fields. So the difference that now I have the pullback of the canonical symplectic form to the primary constraints submanifold. And in such a way that the field that I find as a solution to this is tangent to this maximal submanifold. So if I can find such a submanifold, it's possible to prove, and this is non-trivial, it's not obvious and it's not trivial, and actually the proof took some time, that if you consider the integral curves of this vector field on this submanifold and project them onto Q, you get something which is strictly equivalent to the Lagrangian dynamics for the system coming from the Euler Lagrange equations. Let me show you a picture of what this statement means. So what you have to do is you try to solve that equation for the Hamiltonian vector field on the whole M0. Generically, that is not possible. Generically, the only thing that you can get is a vector field over an inclusion path defined by some submanifold that I am calling M1. So pictorially something like this. So I can only solve that equation not on the whole M0, but just in some submanifold. And then what happens is that even though those vectors, all these vectors, are tangent to M0, they are not tangent to M1 everywhere. So I have to look for another submanifold, this time of M1, which I am representing in this way, that satisfies the condition that this solution that I found is actually tangent to that submanifold. If I can prove that this is the largest submanifold in some sense, that is what I need in order to describe the dynamics of the system. Comments on this method. Of course, there are some disadvantages. Let me put it that way. If you are only interested in the dynamics, Hamiltonian dynamics, then it will give you something equivalent to the Dirac method, and actually in practical terms it's better to use it. Of course, if you want to quantize, you may have a problem because even if the canonical symplectic form is a very simple object, the pullback of this symplectic form to a primary constraint submanifold may actually be more complicated. So in practical terms, if you want to quantize the system, you may run into trouble. So this one must take into account. It's also true that once you get the constraints in this G&H approach, these are always equivalent. They describe the same submanifold that you will get from Dirac's method. So you can always backtrack and say, well, okay, I have these constraints, now I go back to the full phase space and do the quantization as I would do it by using Dirac's method. So it's not a big Hamiltonian, but it may not be really advantageous to work with a pullback of the symplectic form. Okay? Now, in order to understand, what, for example, how constraints appear in this setting, you have to realize that this pullback is generically degenerate. So it may happen that the solutions to these are not unique. If that is the case, then you have a H theory, and the arbitrariness in the solutions to the Hamiltonian vector fields is actually H-free. Okay? Also, it may happen that because this is inhomogeneous, actually in order to solve it, you need some extra conditions on the image of the map that you have here. So that is the origin of the second band constraints in this setting. The consistency of the dynamics, and this is a very important point, which seems trivial, but it actually has important practical consequences. The consistency of the dynamics that usually Dirac faces as saying that, well, I must show that the constraints are preserved by the evolution defined by the total Hamiltonian, things like that. here it turns into a very easy geometric condition, which is tendency condition.
Question?
Yes?
Isn't finding this submanifold N solving the secondary constraints?
No, it's not solving, it's finding.
Or finding solutions to the secondary?
No, you're not finding the solutions to the secondary constraints. You're actually finding the form of the secondary constraints. So in that sense, it's not better than what you would find by using the next method. So it's actually a procedure. I mean, the extra conditions that tell you what these final manifolds are the secondary constraints.
Okay, but once we determined N, did we restrict ourselves to N only, or we still work on some?
That depends on what you want to do. It is exactly as in the that case. So if you manage to solve the secondary constraints, and if you're clever enough, you may find some nice way of parameterizing the final constraints of manifold and then express everything in terms of these three parameters. That will be perfect because that will give you a complete description of the reduced free space. Usually you cannot do that, and then you have to leave the constraints as you would do in the case of the arc. So the final result in that sense is exactly the same. And the same difficulties that you have in one case, you have in this other case. Okay? Okay. So what I was saying is that the fact that the consistency can be understood as just simple tendency conditions actually has some concrete consequences. One of them seems to be a silly one, but when you deal with concrete examples, it's actually important. And it is that the computations are much shorter. You write much less, so that is very good. And the second one, which is slightly more subtle, but it is important, is that you can actually avoid the use of Poisson brackets. So to check tendency, Poisson brackets play actually no role whatsoever. Now, if you have no problems computing the Poisson brackets, then it's fine. But if there are some difficulties computing Poisson brackets, and this happens, for example, or may happen when you deal with field theories with boundaries, then this fact actually will save you a lot of suffering and problems. Okay? So let me illustrate all these things with a very simple example, which is the following one. Let's consider a massless scalar field. You find an interval, so you have a spatial manifold, which is one-dimensional, but has boundaries. And let me introduce boundary conditions, so the Dirichlet homogeneous boundary conditions, in the following way. Instead of just saying from the start that the configuration variables are some scalar fields that vanish on the boundary, I will consider arbitrary scalar fields in this interval. But then I will write an action that will give me these Dirichlet boundary conditions when I compute the variations and I compute the overall equation. So the action is the following. It's given by the usual Lagrangian, and then I add an extra field, then call it psi, and this total derivative term. Now, when you compute variations, so I have two scalar fields, but you have to remember that this guy is an arbitrary object that I am using only to enforce homogeneous negative boundary conditions of the one. Now, when you compute the variations of these, you can see that you get the wave equation in one dimension, and you get these other conditions. It's very easy to see because, of course, you can integrate this part here. You will get the value of the product at 1 and at 0. And if I think of the image of this field at each point as independent degrees of freedom, of course, the variation with respect to psi 0 will give me the condition phi of 0 equal to 0, and a similar thing at the other side. So in practice, the value of this auxiliary field at the boundaries is working as some Lagrange multipliers that enforce these Dirichlet boundary conditions. Okay? So this does what I want. Now an exercise, an interesting exercise, in fact a challenge, is to try to use Dirac's method to expand this problem. I will not go through the details, but I will tell you why this is not so easy and not so trivial. There is actually a nagging difficulty that you find when you try to do the computations, and the difficulty stems from the fact that sometimes you get such Poisson brackets, and usually you get them inside integrals. So even, I mean, if you take this as delta of x0, it's sort of okay. But then in the same formulas, you also get objects such as this. And this is really a problem, because if you write the Poisson brackets like this, these are not defined if x is equal to 1. Now, the standard law is that, well, I mean, this way of looking at Poisson brackets is a little bit too naive. To have to actually think of a smear field, and when you smear the fields, there is no such a problem. But smear doesn't work very well here, because precisely of the boundaries. What happens is you have an delta which is sitting on the boundary. You see, when you integrate that, what do you get? So it's not really well defined. And actually, it doesn't help to solve this problem here. So it's a mess. So and actually, there are published papers where people, with lots of citations, where people have tried to apply the Dirac method to this. I cannot understand them. They get the right result, but probably because they knew it in advance. You follow the reasoning, at least to me, it's completely opaque and probably wrong. Okay? Now, what is the problem? The problem is that in this case I have a boundary, and if I have a boundary, I have to be careful with the computation of the Poisson brackets. Now, one thing that one may say in this, in an example such as this, is that, well, of course, if you want to compute Poisson brackets, you must check, for example, that your functions are differentiable in the first place. If they are not differentiable, if they are not smooth enough, then you will not be able to compute them, and then maybe this is what happened, or it's happening here. Okay. But then it so happens that in the context of gravitational theories, for example, when you introduce boundaries, people actually talk about differentiability with a meaning which actually doesn't have anything to do with the standard mathematical sense, which is what I call Frechet differential. In particular, this happens in the context of you study gravity and you have boundaries, and you consider boundary terms as regularly treatable. These are a long time ago. So let me just digress a little bit here to say a few words about differentiability and where these problems come from, and then I will go back to the example and show you what you get when you use this image method. Now, this is a standard differentiability definition of differentiability. I assume that here in Poland you learn these things in kindergarten, so I will not go through this. But this is just a standard concept that you may use, for example, to define differentiability in multivariate calculus. Now, of course, a differential is a linear approximation, linear and continuous approximation to a function that satisfies this condition here. It's easy to prove when you work with finite spaces that this thing is unique, for example. It's trivial to show that if you are computing the differential of a linear and continuous function, then it coincides with itself. It happens with identity, for example. This is a very useful concept, and there are many theorems that even existence and uniqueness theorems for differential equations, something that you may need, for example, to talk about the integrability of vector fields, that really rely on this concept. Okay? And this, of course, is a kind of differential that you use to define the stereo derivative in differential geometry, which is a basic object in Hamiltonian mechanics, as I showed before. And in the context of the Lagrangian and Hamiltonian formulations of gravitational theories, there is another concept of differentiability that I call, together with some, also in Mexican, it's TINA, so probably came with this before we did. Reiterated with differentiability. It appears, for example, in Holst's book, and it means the following. You give me a function on some space of fields, defined on a manifold with a boundary. This other concept of differentiability means that if I compute variations of that function, those variations don't have a surface term and can be written in the following way. When that happens, the people say that this thing is the functional way. Okay. But of course, if you think about this and you compare this definition with the standard Frechet derivative, the differential, these things have very little in common. So you must be very careful if you are dealing with theories with boundaries, and you have to compute, for example, functional derivatives you have to discuss the differentiability of your functions because you want to compute Poisson brackets and things like that, it is at least dangerous, and my impression is that you will always make mistakes, to conflate this type of definition with what you find by using the standard fresh-head differentiability concept, okay? So this is really very important in the computation of Poisson brackets in theories with models. And why is that so? Because, well, the kind of formula that we usually have in our minds when we want to compute Poisson brackets in the theories is something like this, that we actually get by some straightforward substitutions from the standard formula that you get in the context of mechanics. But then, of course, you have to be careful with what you put in here. And also you have to be careful in the sense that, well, these products here actually look like two scalar products, but there may be other contexts where they should be interpreted in a different way. I will not talk about that today, but I can, if you are interested, I can give you some details about that. Okay? So let me go back to my example. The morale of what I'm trying to tell you is that if you use this G&H method, you can avoid this, in this particular example, you can avoid all this discussion about how I have to compute the functional derivatives and so on, precisely because the consistency of my Hamiltonian formulation consists really in checking that some tendency conditions are satisfied. So you can avoid, in this case, completely the discussion of Poisson brackets. Then when you go through the full procedure, you find the following. I will just describe the result for you, and there are some slightly surprising things in there. So you get the primary constraint, which is telling me that the momentum canonically associated to this auxiliary field that I introduced to implement the homogeneous Dirichlet boundary conditions is actually zero. Of course, that also this must happen for every time, so that means that the component of the vector field that describes the dynamic associated with this is also zero. Now, despite the fact that this is a scalar field, which is not a HDA fund constraints, it's a singular system, I find a set of secondary constraints, and these are very interesting. The first ones are just the boundary condition. That's okay, that's expected. But then there are two infinite towers of constraints involving the even derivatives of the field at 0 and at 1, and also the even derivatives of the momenta at 0 and 1. These are not so easy to guess. It is true that if you go to the mathematical literature, even in undergraduate courses on partial differential equations, mathematicians know that these things are there. They don't arrive at them by using the Hamiltonian method. They do it in a different way, but this is not. If you go, for example, to Brex's book on functional analysis applied to partial differential equations, when he discusses the wave operation in 1 + 1 dimension, he shows these things, and he gets this thing completely differently. It is nice to find them when you following procedure adapted to the standard Hamiltonian method. And then there are these other constraints that involve the value of this psi field at 0 and 1. Okay? And then the final thing that you get is the Hamiltonian vector field. Hamiltonian vector field has components associated with the field phi, the momentum phi associated to phi, and then also the psi field and its momentum. One of these, part of these components actually give you the wave equation. Of course, it should be there. And then there are some others that actually just tell you what the dynamics of this auxiliary field on the boundary is. Okay? And of course, you see that there is no arbitrariness in the components of the Hamiltonian vector field, so this is not an H theory. There is no arbitrariness at all. But it is a singular theory with constraints, and these constraints are these towers that I have shown you there. Now, it's very nice, there is a nice interpretation of these that I will show you. So this is something that has a meaning, and a simple way of understanding that is the following. Consider now that you want to construct the solution of the wave equation for some initial data, which is this red function here, and with zero velocities. So I just take my initial value of the scalar field t, and the time derivative is zero. Okay? Now, a neat way to build solutions in 1 plus 1 dimensions is using this Barbero formula, and in order to compute the solution, what you have to do is the following. You halve the value of the function, and then you extend it periodically to the right or to the left. Now, this function, this standard function, you evaluate at x plus t, say, and x minus t. You add those things, and that, first of all, guarantees that it is a solution to the wave equation, and second, because this extension is odd, you always guarantee that the boundary conditions are satisfied. So you start evolving, you have to displace to the right and to the left this extended function that I go, and you will be getting something like this. And an important comment is the following. This point here, which is the point where the extension matches the value of the initial function inside, if you want that your solution is always smooth, for example, you must guarantee that this extension is smooth. Otherwise, you may have some jump in some derivative. Okay? Well, but then what happens is that these conditions here, and the other ones in the momenta, are precisely the conditions that you need to guarantee that this extension is smooth. So these secondary constraints that you find by using this D&H method, in this particular case, actually have a nice interpretation. These are the conditions that your initial data are satisfied in order to guarantee that the solution inside the interval is always smooth. Okay? So this also shows in this very simple example that this method, this D&H method, is actually quite powerful because it somehow goes beyond what you would expect. It can say something, for example, about the smoothness of the solutions, which in principle is not a kind of abstract property that we would expect to be described by some constraints. Okay? So this is this thing. So I will end this part with some comments. So this infinite tower of constraints is very difficult to find by using the Dirac method. Mathematicians know that they are there and they can be found by using this way. They are important, I have just justified. As a practical thing, both the constraints and the Hamiltonian vector field that gives the dynamics can be obtained without caring about the Poisson brackets. So if there is some difficulty with them, as it happens in this particular case, you don't have to worry. So in some contexts, you can actually avoid some issues related to functional analysis that I will mention very quickly in the end if you use this method. Okay? You want to see particular examples, you can, this is a reference where we discuss this. Now we'll talk about another application of this D&H method and a slightly different point of view regarding the Holst action. So the Holst action is one of the basic actions that you can use to arrive at the Ashtekar formulation of your relativity, the real Ashtekar formulation. It has been studied by using Dirac's method, and the results are correct. The only complaint that I have about those results is that when they just get the last batch of tertiary constraints, they get them in a very, very complicated form. So it's something that's not transparent at all. Whereas if you use the D&H method, you can actually arrive at a much nicer version of, equivalent version of those constraints. Okay? Now, in this particular case, actually there is a neat way of understanding what's going on, which somehow suggests a slightly different procedure to get a Hamiltonian formulation for some field theory. So I will describe it here to you. So you can do the following thing. You can take your Holst action, you have the field equations, you will write the action in the space-time, which has the form sigma cross R, so you have some three-dimensional manifold, which I will take closed, compact with a boundary, and just the product with R. And then you, of course, you can introduce a formulation and perform a 3 corresponding position to find the Lagrangian. Once you have the Lagrangian, you can find the final derivative, the delta, define the primary constraints and manifold, get a Hamiltonian, pull back the canonical symplectic form on that. So that is exactly what I have described now. And now you have the following possibility. You can go to the field equations, which in this particular case are very neat, because the action is written in terms of differential forms, and I will show you exactly how this works. And then you can do the following thing. You can take these equations and pull them back onto the sheets of the formulation. So that will give you constraints, which should appear when you do the Hamiltonian analysis. Actually, they do, and when you use this derivation method. And alternatively, you can first project the equations in the direction of the vector field defined by the type that you have here. I will also show you how that works. And then project them onto the sheets of this manifold. By doing that, you get the expression of the components of the Hamiltonian vector fields. And once you have that, you can actually see if this tangency condition that you need to, in order to guarantee the consistency of the dynamics, holds. And you can check in this case that it does. So this is something like a shortcut to arrive at the same formulation that you will get from the GNH analysis, but it is simpler in the sense that, as I will show you, the complicated constraint, something, the really difficult part, both in the Dirac analysis and the GNH analysis, is solved like, it's solved magically, I would say. So let me explain this thing in more concrete terms. This is the Holst action. The Holst action defined on this manifold, where sigma is closed. Here, the EI are non-degenerate tetrads, so there are 4 one-forms. This capital index goes from 0 to 3. You can define also the curvature and SO13 connection, so I'm working with the Lorentzian case. And this object here is has this expression, and it is built in terms of the Levi-Civitas symbol to Minkowski metric and depends on the municipality. So this is the Holst action. Now, when you compute the field equations, this is what you get. Okay? These equations are the same that you get from the Palatini action, which is the action where you just drop here the terms coming with the dependent on the municipality method. Now, there is a very interesting observation that one can make here, which is that these equations are strictly equivalent to these other ones. The second is the same. As you can see, the first is simpler, and it's not quadratic mean, but there's linear mean. It's not difficult to prove this equivalence. Actually, I don't know who realized, who were the first people to realize that it was possible. I definitely read that in a paper by Cataneo and collaborators. You can convince yourself that this is possible because when you count the number of equations that you have here and you have here, the formulations are actually the same. Okay? This has very interesting consequences if you think in the terms that I discussed before. So let's suppose that I take my manifold, my spacetime. This, of course, is naturally foliated by hypersurfaces, three-dimensional hypersurfaces given by these sets. Okay? So these are this time formation. Now, of course, I can define in a very trivial way a scalar field here, which is basically given by the value of whatever actually are. And also I can find, there are some natural curves that I have in here, which are those for which this base point that I here is just the same. So I have a components of curves, which are parameterized by this function. I can, of course, compute the tangent vector, and that defines a canonical vector field, which is associated with this other time variable, which I call partial field. So these are canonical natural structures where I have this structure in my space. Okay? I consider the inclusion of each of these sheets into the space-time manifold, and I define these objects. So you see I am projecting in the direction of this vector field, and pulling back with, by using this inclusion here. There is a typo here, this formula should not be there. These two guys are just functions in every sheet of the formulation are these two other objects, which I'm writing in. I'm not using the bold phase and I'm writing them in green here, but in the rest of the talk I will just remove the bold phase. So these two guys are non-formals. Okay, so now, suppose that we do what I said before, that I take the equations in this form, the second form, not in the first form, and I pull them back onto the sheets of the formulation. If I do that, I get these things, which I must interpret as constraints. So these involve these three-dimensional objects which are still labeled with these four indices, with these indices going from 0 to 3, okay? So I get these constraints, which are exactly what I get if I'm clever enough by using the GNH method. And then if I do the other thing, I first take the equations, I compute the interior product with this vector field, and then pull back onto the sheets of the formulation. I get these equations, which are actually evolution equations. In fact, for the first one, I can read exactly what the component of the Hamiltonian vector field given the evolution of E is. In the second case, I have to solve this equation because I have something multiplying omega naught, which is a derivative. But that's easy, so you can do that. And you get that these guys are arbitrary, which is actually what you expect. And from here, you can actually read the Hamiltonian vector fields on the primary constraints are manifold that are tangent to all the constraints and describe the dynamics of the whole function. This is straightforward, and this is exactly what you will get if you use the GNH method. Now, there is something funny going on here, which is one of the surprising things of this system, which is the following. When you look at the equations, if you remember, I told you that the number of equations here and here in 4 dimensions is exactly the same, no problem. But when I pull back, if I pull back this condition, then I get only 6 independent equations. I mean, the content is very simple. You have just to take into account that this index goes from 0 to 3, but now these guys are there are non-folds in 3 dimensions. So they are 3-dimensional objects, not 4 dimensional. On the other hand, if I take the equivalent form of equations, which, if you remember, d equal to 0, and I pull back those onto the sheets of the formulation, I get 12 equations. So magically, because of this magical equivalence between the equations with the E here and without the E here, when I pull back, I get double the number of constraints. And this is very interesting because the extra constraints actually correspond to some tertiary constraints which are very difficult to deal with, both in the method and also in the GNH method, where things are really simple. So, one of the lessons that we learn from here is that if your theory is written in terms of nice fields, for example, differential forms, and something like this happens, that you can somehow simplify the field equations in this way, you can actually guess very, very quickly some of the secondary or tertiary constraints that you will find in Hamiltonian analysis without making a terrible effort. Okay, so that's for us. So finally, what do you get if you follow this approach or the GNH approach? So what you get is what we call the concise formulation, and it can be summarized in a few lines. So your phase space, which is actually a primary constraints of manifold, is spanned by these objects. So you have no momentum. It's only these E's and these omegas components. There is a Blessing-Lectic form which has this structure where this P tensor appears, and if you remember, that depends on the immiscibility. Now the constraints have this form, and these are for Lorentzian GR. So if you think of the constraints in any formulation of GR, real formulation of Lorentzian GR that comes to your mind, they are all more complicated than these. Of course, in geometrical dynamics they are, but also if you go to the real Ashtekar formulation, there the Hamiltonian constraint has a complicated structure. Here in this setting, they are as simple as they can be. This defines these constraints on manifold that Glenn was asking about, that is really what the dynamics happen. This is a Hamiltonian, which vanishes n, and the Hamiltonian vector fields are obtained by solving this equation. I can give you the explicit form, but it's not very illuminated, so I will not do it here. Now, an application of this formulation, which is very compact, you can actually use, for example, to derive the Ashtekar formulation. And this is an interesting computation, and it's a good exercise, so I recommend you to do it. The procedure can be summarized in one of the slides. So what you have to do to arrive at the Ashtekar formulation, the real Ashtekar formulation, for Lorentz and gravity, is the following. You separately consider the capital I equal to 0 and capital I equal to 1 to 3, so these components, and introduce a time gauge. So you have, so you have to take everything as a manifold of n, which is defined by this acceleration. Now, from this part of the constraints, you get this equation. So the other components of this constraint here, this one, you get this other equation. Another key step is the following. You solve the first equation for omega. You can write omega in terms of its dual that I am calling gamma, and solve for this in terms of E. And you plug, for example, this into the symplectic form together with the time gauge condition. When you do that, you find exactly this expression. And from here, you can read off immediately the change of variables that takes you to the Ashtekar formulation. This is the Ashtekar collection, and this is the trial. Okay? Actually, if you look at the expression, something funny happens. So when you multiply these terms, this gamma and this gamma go, so there is a term which is independent of gamma. Apparently there is a gamma dependent term which comes from this multiplied by this, but actually that term is 0. So here, in fact, even though this is given to the Ashtekar variables, actually this symplectic form is independent of the implicit one. Okay. Now, once you have these variables, if you plug them here in this second equation, you get the Gauss law. And if you plug them here, you get the vector constraint and the Hamiltonian constraint for the real case, which, as you know, has an ugly and complicated structure. So I will finish with a couple of slides. First one, some comments about this concise formulation. So you can get this by using G&H method. No problem with that. It's complicated. If you look at the papers, in particular this one, you will see that it's not trivial. There is this funny way of arriving at the same thing by looking at the field equations. My advice is that for simple theories, it's actually interesting to look at the equations just to see if you can get some information about some constraints that may appear as secondary or tertiary constraints and may be difficult to obtain. Okay? An interesting comment, which I still don't know what the physical meaning is the following. The immediacy parameter, it only appears here. Okay? But when you pull back this symplectic form to n, to the final consensus manifold where the dynamics happens, the immediacy parameter disappears. Okay? So that somehow suggests that, well, if you manage to quantize in this space, then the immediacy parameter may appear in the quantization, but if you could really work in the final consensus manifold, the immediacy parameter should not appear. So there is something that I don't understand regarding that. One thing that I would like to tell you is that I think that this concise formulation is very nice, and it's very, very simple. It's structurally the simplest thing that we can think of. It works because you can get the Ashtekar formulation. So an interesting problem is to see if one can use it for compensation. I understand that this is not easy because this is not a canonical symplectic form, but actually more complicated presymplectic form. It has the general dimension. And then final slide, and I will finish. I mentioned several times during my talk functional issues, so those are important. Actually, we've been working also on this, and we know that they may play an interesting role. The generic comment that we can actually do for every field theory is that the details of the functional spaces may be relevant, and not only for a mathematical rigor, but also to do concrete computations. These geometric methods that I have shown you are sensitive enough to say something about these things. In particular, for example, about smoothness, as I showed in the case of the scalar field, but also other things. If you are careful and you work with nice spaces, for example, solid spaces, you can actually avoid the use of these solutions, which may not be useful, for example, to understand quantum field theory. And it is not out of question that, for example, regularization procedures in these spaces can be understood from a different perspective. Okay? And as a final comment, I think that this is not just a matter of mathematical rigor, but may have some practical consequences. And I finish here. Thank you.
Questions? Comments?
I mean, the computations will be the same. So if you complexify, I don't see that nothing significant changes. And even, and you can do those also in the Euclidean case, real Euclidean case. So from the point of view of what you get and these geometric procedures, I don't think that there will be a significant difference. But I would need to think about it. But my guess is that it is not, nothing changes. Okay.
Thank you.
Does your approach allow generalization to dimension higher than 4? And if it would reproduce the schema's way of generalizing Ashtekar formulation to higher dimensions, so you could maybe propose something different from that?
Okay, so do you mean if I take the Holst action, for example?
If I mean, it's only a problem how to generalize the
Okay, I think you can. So this miracle that the field equations can really be simplified to this d equal to 0 form, as far as I know, only works in 4 dimensions. So if you go to higher dimensions, of course, I mean, you take that action and you go to higher dimensions, you can always use either the Dirac method or the G&H method and find the constraints. And actually, once you know that some tertiary constraints can be simplified in the case of non-degenerate tetrads, or 5-ads, however you call them in 5 dimensions, then actually that may tell you how to proceed to really arrive at the simple formulation. So that's probably the case. But this trick may not work or may work in a different way. So you may be able to simplify the equations in different dimensions to get something which may not be of the simple form the e equal to 0, but maybe simple enough to give you extra constraints when you use this pulling back process that I described. Okay?
Thank you.
Well, let us thank the speaker.